Okay, good afternoon, everyone. I am Moshe Matalon from the University of Illinois at Urbana-Champaign. As you see in this map, Urbana-Champaign is located somehow in the middle of Illinois between Chicago and St. Louis. I'm in the Department of Mechanical Science and Engineering, which was one of the probably biggest department in the College of Engineering after computer science and electrical engineering. And the school encompasses almost 12 departments. It's quite a large school, highly ranked, most of you probably heard of. So I want to say a few things about theory before I start the lectures. And you see, our ultimate goal is to make predictions of combustion systems. And for that, we need theory as well as experiment and simulation. And you see, all of them feed into the knowledge that we can accumulate to make good predictions. But of course, theory is helped by experiment and by simulation, and similarly, all the others feed into each other. And so the element or the ideas, the concept that I will be presenting will be essentially in this box here during this week. Before we get serious, I just want to make a quick, I want to put a quick poster that I saw or I found in a small store when strolling the streets of Paris. And I don't know who the author of this is. This is a picture of the little poster I said, and loosely I translated as follows. The theory, it's when we understand everything, but nothing works. In the practice, or if you like, application, is when everything works, but we don't know why. And the poster said that here, and I don't know where is here, we have succeeded in both nothing works and nobody knows why. And so hopefully we will try to understand a little bit of why things may work. So first, I would like to start with a few comments about theory. You see, and most of my slides, by the way, will be the other way around, so it's only the first few like this. So I think it will be clearer. As we shall see today, the mathematical equations that describe combustion processes are very complex, and we often make a lot of approximation even to come to a system that it's manageable computationally or numerically. Clearly, if we want to do some theory, we have to take even more serious steps in making some assumption. And so that's where you see here I do. Okay. I'm not used to this, so it would take me a while to go through it. So, we try to build simplified models by removing some of the details and retaining some of the key important factors. And the most systematic and best way to do it is by the use of perturbation method and asymptotic methods, because that's the way where you get a good gauge of the different terms in the equation, and you know what you could or could not simplify or could not neglect. Otherwise, you do it in an ad hoc way, and you really don't know if that is an important effect or not. And such simplified models are useful because they are simpler than the full equation. They require perhaps, even if they are not solvable analytically, they still can be solved by simpler numerical methods. And they can lead to full parametric dependence of the solution, something which is hard to do if you try to do direct numerical simulation or in general simulations. Usually you solve the problem for a certain set of parameters, But here you can stretch it to the extreme, and sometimes it's very useful to do it in the extreme, even to those range of parameters which seem to be not physical at first. Sometimes they may be relevant in some particular cases. So it's important to be able to understand fully the nature of the equations of the model that you are trying to solve. As I pointed out here, they identify key physical mechanism, which are the important mechanism in a given process, identify cause and effect, explain and guide the experimental studies, and I can show you, or I can mention perhaps at the end of this week examples where, if I will have time, perhaps I put this slide back and I will show you examples where these elements were indeed useful in our understanding today of combustion processes. Often we derive useful expressions that can later be used in correlating experimental data, and certainly they can guide the DNS and can be used for validation in special cases. So with these comments as introductory, I would like to start with the first lecture, which is the governing equation of combustion system. And so I will start with really talking about equation. I am not sure the background of everyone here in this room, so I will very quickly describe the governing equation in fluid mechanics of a pure substance, namely one species, not a mixture of various species, and then we will go into a mixture and see how the equation generalizes in that case and how they become more complex. So in fluid mechanics, we focus usually on a material volume, Vm, which is made of the same fluid elements or the fluid particles. So for mass conservation, say we write that the time derivative or the time rate of change of the density or the mass of that volume doesn't change, is conserved. But that volume changes in time, and so the derivative of an integral of a volume that changes in time need to be determined, or have to determine how we take this derivative. And for that, it goes really straightforward from the definition of derivative. One can derive the expression here in this box, which is the time rate of change of a quantity which the volume change in time. It's equal to this volume integral plus a contribution that comes from the fact that the volume moves, and therefore there's contribution from the surface. Now, when this VI is the velocity at which the interface moves. Now, if VI is equal to the gas velocity or to the fluid velocity, then this is usually known as Reynolds transport theorem. But this statement is correct even for an interface or a surface that move at any other or given velocity. And by the way, this is the analog of a simple rule in calculus, which is known as the Leibniz theorem, which is just the derivative of the integral, say, from a to b, where a and b are both depending on time. So usually you have the derivative of the integrand plus some contribution that come from the fact that a and b are varying. So it's the same thing as the surface integral here. So here is again that expression. And as I said, it's Reynolds transport theorem when the VI is replaced by V. And in this case, one can also write equivalent form to that expression by using the divergence theorem to replace the surface integral with a volume integral. So you see that's a volume, it's a divergence of the quantity phi times V. And there is a third form here that can be also expressed. We are going to use primarily the second one in the discussion that follows. Note that I have used here the notation capital D by dt, which is the time rate of change following the fluid or following the fluid particle. and it's usually referred to as the convective or material derivative. So for example, d rho by dt will be the time rate of change of the density following the fluid particle. So it's written as that expression, which is the time rate of change of the density at a given point, plus the fact that the fluid is moving and there is a contribution, this convective term. Similarly, if it's applied to the velocity, it's going to be the acceleration of a fluid particle. The first statement is one of conservation of mass. So we write d by dt of the mass of the volume is conserved. And then if we replace the integral, the derivative of this integral on the left by using the Reynolds transport theorem, we obtain simply an integral over the fixed volume, right, of d rho dt plus the divergence of rho v. But since this expression is true for any volume, then the integrand must be 0. And the integrand 0 is the well-known continuity or conservation of mass equation. Okay? And there are different ways to write it. Another way is to use the product rule on the divergence, which split into two terms. So the first term is just the material derivative or the convective derivative of the density, and the second term is the dilatation or the change in the expansion or change in volume. And so if you rewrite this expression in this form, you obtain that the rate of compression or the rate of dilation is the time rate of change of the density of the density of the fluid parcel. If the density remain constant, we talk about an incompressible fluid, and the equation is simply that the divergence of V is 0. Now we do the same thing by applying Newton's law to the material control volume. So now we look at the time rate of change of the momentum, rho v. And the time rate of change of the momentum is going to be equal to all the forces acting on this fluid parcel. And the forces are usually divided into two: a body force, which it's like gravity, so it's acting everywhere on the body of fluid, plus a surface force that acts on the surface of the fluid volume or the control volume that we are looking at. So T here is a vector which corresponds to the forces acting on the surface S. And remember that both V and therefore S are changing in time. First of all, we can rewrite normally T is expressed in terms of 9 components, which are represented as a tensor, which is the tensor sigma, and that's the stress tensor. But sigma is usually symmetric, so there are in fact only 6 independent components. Now, if we, so when we express T in terms of the stress tensor, the equation above reduced to the one here. Again, we apply Reynolds theorem on the left side of the equation, which give us the first 2 terms, and then the other 2 are put on the same side of the equation, where the divergence theorem was used here to represent the surface integral in terms of the volume integral. So now again we have the integral over a volume of a certain quantity, which is equal to 0, and since it's true for any volume V, then the integrand must be 0. And that reduced to the momentum equation, which I will write in a minute. But just note that this rho VV is the momentum flux tensor. It's a tensor that contains, again, it's like a matrix of 3 by 3, right? And the components in terms of indices are rho VI, Vj, right? Okay. So here is the integrand, which is equal to 0. And it's written in the form that the time rate of change, which is in fact this, I'll make a comment about this in a minute, is equal to the body force plus the surface forces acting on the fluid particle. And from moving from here to here, one needs to use the fact that the continuity equation is satisfied. In other words, you use the product rule on this quantity and that quantity, which reduced to simply rho times the material derivative on V. I will make that comment again soon because it's an important one the remaining of the derivation. Now, one need to describe the stresses in terms of the fundamental fluid properties, namely the velocities. And what you have here, it's a constitutive relation. It's an assumption, if you like, or it's one which is obtained just from practice. And that equation is, assumes that the stresses are proportional to the strain, and it's known as a Newtonian relation, or therefore the fluid that obeys that equation is known as a Newtonian fluid. And the stress tensor is therefore written as the pressure. I is a unit tensor, so it's minus P times just unit tensor I. And the remaining part is the viscous stress tensor. When it's related, as I said, to the velocities, is essentially obeying Newton's law that it's proportional to the gradients of the velocity. And what you see here, it's this is known as a dyadic. It's like a tensor. The T here is a transposed. So in terms of component, this is dvi dxj, and this is dvj dxi. And this gives you the component sigma ij of the viscous, of this part of the viscous stress tensor. Then there is another part here, which is the divergence of V multiplied by this kappa, which is known as the bulk viscosity, and mu, which appeared also in front of this one, is at the shear viscosity. Now, since this quantity is a scalar, it's multiplied, of course, by I, which is a unit tensor, so you have a proper equation, if you like. So if we substitute that below, we have the momentum equation, which is the density times the acceleration of the fluid particle. It's equal to the pressure gradient, the viscous forces, and the body forces. And I don't have to move there. And now we move on to conservation of energy. So again, we write that the total energy, which is the internal plus kinetic. So ET is the total energy. It's the internal energy plus the kinetic, which is 1/2 V squared. In components is V dot V in vector notation. So again, we want to calculate the time rate of change of the total energy inside a control volume, a material control volume. And that should be equal by the first law of thermodynamics as the rate of the work done on the volume, V by external forces, which is going to be both the body forces and the surface forces, plus the rate of internal energy flux across the surface. And so this is written here. You see here is the contribution of the body forces, the contribution of the surface forces, and the heat flux vector Q dotted with the normal, which is what enters or leaves the surface, is the contribution of the internal energy. It's the flux through the surface S. Q is written always such that it's positive when the transport is outward, and hence the negative sign in the equation. Now, we can use the divergence theorem to rewrite the surface integral into a volume integral. And similarly, after substituting for T in terms of the stress tensor, again, we can use divergence theorem to write that as the integral over volume of the divergence of this quantity. So now all the quantities in this equation, well, except the first that we have to apply again Reynolds' theorem to express the total derivative of this material volume, which is, as you see, it's expressed here by the first two terms. And then everything under this integral, a quantity, or this whole quantity is an integral over the same volume. Again, it's valid for any volume, and therefore the integrand must vanish. And if the integrands vanish, that's what you get on top. It's a rewrite of the previous equation. And now remember that this is the time derivative of the total, or this equation was written for the total energy, right? Kinetic plus internal. So the next thing that we do is we we replace, which is written here, by the way, internal plus kinetic. So the next thing is we want to remove the kinetic energy part from this equation. And the way to do it is just to take the momentum equation, multiplying it by V, because the momentum equation is essentially rho dv dt. So you multiply by V, and you get, with appropriate manipulation, of course, you get an expression for the time rate of change of the kinetic energy. So if you remove it from this equation, you end up with an equation just that tells you the time rate of change of the internal energy E. And the first two quantities, by the way, just to see that everything is consistent here, which is an important check always when you write any equation, is to see that sigma is a tensor. You dot it with a vector, so you obtain a vector. You take divergence, you obtain a scalar. So of course you expect that this equation is a scalar equation. It tells you the time rate of change of energy. And the first two terms combine into, well, it's this operation that you start with a tensor and a vector, and you get the scalar is known as a contraction operation. Sometimes it's denoted by this 2 dot. But the main point is that this contribution here involves two terms. One is the work due to the pressure, and the other one is due to the viscous forces. And the phi, I didn't write it explicitly. I will write it later. It's usually known as the dissipation function. Okay, so we have now this energy equation, which involved the work done by the pressure, the viscous forces, and the heat transfer to or from the surface, depending on the sign. Now, all these equations involve quantities that we didn't have expressions for them, like internal energy and so on. And so we need to bring in some elements of thermodynamics to complete the system. And so here is very a quick review, if you like, of thermodynamics into 2 or 3 slides. First, remember that we are talking about pure substance. So the state of the gas is uniquely determined by 2 variables, which is basically a statement of that you start in when you discuss thermodynamics. For example, the pressure can be expressed in terms of density and temperature, the internal energy in terms of the pressure and temperature, and so on. In particular, if you're talking about an ideal gas, then we know that the equation is P equal to rho RT divided by W. R is the universal gas constant, W is the molecular weight. And so you see that pressure depends on 2 other variables, rho and T. But there are other thermodynamic variables that we did not encounter so far, which are also determined by some of the following relations. So for example, we often use enthalpy instead of internal energy, and the definition is that the enthalpy is the internal energy plus P over rho. Or we can use one of those 2 relations to determine the entropy of the gas. And everything here written in lowercase is identified as a quantity per unit mass, not the total entropy. So often referred to as the specific entropy or specific entropy and so on. So we talked about ideal gases, and we will only focus on ideal gas. Another important thing about ideal gases that the internal energy and therefore the enthalpy are a function of temperature only. Well, if you start with this fact, then the fact that enthalpy depends on T is obvious simply from the definition, right? Because P over rho is RT. And so they depend only on temperature, and one therefore introduce the quantity which are known as specific heats, Cp and Cv, specific heats at constant pressure and specific heat at constant volume. And so for an ideal gas, Cp is defined as the derivative of H with respect to temperature, dH dt, and Cv is defined as dE dt. So if you integrate this equation, you get that the enthalpy is written to some integration constant that I called H subscript naught, plus the integral from some reference T naught to T of Cp. Clearly, H naught is the enthalpy at the reference temperature T naught. And for a pure substance, it's totally irrelevant what it is because we are interested usually in change in enthalpy. The same thing with internal energy. We are going to see that when we talk about mixture, then the reference value will be very important. In fact, it's crucial, not only important, to define it consistently. So the next thing to define and often used is gamma, which is the ratio of the specific heat, Cp over Cv. And from the relation or the definition of H, if you like, which is E plus P over rho, if you differentiate this expression, you get that Cp is a Cv plus the specific gas constant. And so Cp is always larger than Cv. Okay? It's always larger, and the ratio Cp over Cv is always bigger than 1. Okay? And with this expression, one can express, those are expressions that are often used in derivation of equation, that Cp can be expressed. In other words, when you have what I want to say is that when you have a gas constant, you can express it in terms of Cp through this relation eliminated from the equation. Same thing with R and Cv. Okay, so now there are a few other forms of the energy equation that one can write. Since I heard you flipping the pages, it just reminded me I have to say that there are some typos that still exist in these notes. And occasionally, there are some differences or additional slides that are not on your note, so just for your attention. If I discover something which is a real error or mistake, I hope I'll remember to mention it to you, but otherwise the differences are not important. It's just more helpful for the discussion. So anyway, this is the energy equation that we have derived earlier. And what I want to show you is just simply that you can rewrite it in terms of one of the other thermodynamic variables. So for example, if you use the enthalpy instead of the internal energy, this is the form of the equation. Nothing changed except the first term on the right-hand side, which in this form is minus P divergence V, and here is the material derivative of dP of P. Similarly, if we want to express the energy equation in terms of the entropy, we get the following form. Again, those two terms remain the same clearly, and it's only the rho T ds dt that replace the first on the right-hand side and the left-hand side. Now, this equation from entropy, I thought it's useful to make a quick comment about it. And this is the following. For a reversible process, namely one for which there is no viscous dissipation or phi equal to 0, then this is 0. Then we see immediately that the change in entropy is exactly related to the heat acquired divided by the temperature. Okay, a statement that is always made in thermodynamics. For a reversible process, for a reversible transition from one equilibrium to another, then phi is not 0. In fact, it's positive. If the process is irreversible, phi is positive, and then the entropy only would increase, which is related to the second law. Another important comment is that for an isentropic flow, namely one for which the entropy change is 0, the entropy does not change, so the left-hand side is 0. What you get is that from the definition of H and the relation that H is related to Cp, immediately you get the following relation. It's just equating the two sides here of the equation, which by integrating you get, this is essentially the logarithmic derivative of P and the logarithmic derivative of rho, which essentially gives you that P rho to the minus gamma is constant, known as the isentropic relation. And one last comment is that the speed of sound, which we will use in few of the discussions, probably tomorrow, is defined as the ratio of the pressure to the density under isentropic conditions. So it's dP d rho for constant S. And so if you use the relation boxed here, you can immediately differentiate P with respect to rho, and you obtain that it's gamma P over rho. So this gives you the relation for the speed of sound. And for an ideal gas, this can be replaced to an expression that depends on temperature, and so it's gamma RT, and R here is, of course, the specific gas constant. Okay, so so far, what we have done is we derived equations for conservation of mass, momentum, energy, and I wrote one of the different forms that I mentioned before in terms of enthalpy. And to complete the system, we need, of course, the definition of H, which is written here in terms of the temperature, and the equation of state that relate the three thermodynamic variables in this equation, namely P, rho, and T. And overall, what we have is 7 variables, 3 velocity component, the pressure 4, 5, 6, 7. And so we need 7 equations to have a closed and complete system. And indeed we have. So here is 1 plus 3 is 4, 5, 6, 7. So we have 7 equations for 7 unknowns, and we have a well-defined system. And in this equation, we had defined already through constitutive relation what the viscous stress sigma is, which is written here, right? We discussed that already before for a Newtonian fluid. And the dissipation function is, of course, related to the component of the viscous stress, and it's just here in terms of indices. And the notation here assume that every time that an index is repeated, you sum over that index. So there is a summation here involved in the first term over I and j. And finally, the only thing we didn't say anything about is what is the heat flux vector Q. And if we assume that the fluid obeys Fourier law of heat conduction by neglecting, say, radiation and other form of heat transfer, then Q is proportional to the temperature gradient. Heat travels or heat is conducted from the high temperature to low temperature. That's why you have a negative sign in front. And the proportionality constant is known as the conductivity, the fluid conductivity. So we have a closed system of equations, and this is for a pure substance. And before I go into discussion of the governing equation for a mixture, I want to make this comment, which I already made, but without showing the details. Note that the material derivative of any quantity phi, which by definition is dphi dt plus v dot grad phi, right? This is the definition of d by dt, or it's a notation if you like. Since I can simply add to this the continuity equation and rewrite that same term as d by dt of rho phi plus divergence of rho phi v, which is often known as the conservative form. So we can write the previous equations that we had by replacing rho the e by dt, let's say, or the h by dt by what's on the left-hand side here. Similarly, rho dv dt for the momentum equation is replaced by this. So occasionally I will use either the conservative form or the non-conservative form. They are equivalent, of course, assuming, of course, that the continuity equation is satisfied. So next we are moving into a mixture of n components in general. We identify the different species that the mixture consists of by the script m. So Mi will be the symbol for species I. So for example, hydrogen, oxygen, CH4, what have you, are this Mi. As I said, the mixture consists of n species, so I run from 1 to n. Now, in order to give a good quantitative description of the chemical transformation in such a mixture, we need to precisely define the word concentration. By the way, here is a statement which was repeated twice in the notes, but I just happened to remember that. So anyway, but it makes no harm. So the concentration is defined as the number of species I is defined as the number of moles Ni divided by the total volume. Number of moles related to the Avogadro number, but that's not important for my discussion here. It's just a general comment. So we can talk also about the mass of species I, and the mass of species I is going to be the number of moles multiplied by the molecular weight, Wi. And so Wi is the molecular weight, and I the number of moles. Now we know the mass, we can divide by the volume and define the density. So rho I is the density of species I. So rho I is mi divided by v. Now if we sum over all I, so the density is rho I, so it's mi over v. V is independent of I, and so it's essentially the sum of mi, which is m. And so what we see right away that this is the total density of the mixture. So the total density of the mixture is the sum of the densities of the different species. Similarly, if we sum the definition, using the definition of the concentration, Ni over V, if we sum over all I and N denotes the total number of moles, then N over V is the total concentration, and the total concentration is the sum of the concentration of the individual species. Now it's convenient to define accordingly either a mole fraction or a mass fraction, depending if you're using the concentration or you're using the mass, Mi. So if you use the concentration Ci of species I divided by the total concentration, that gives you the mole fraction. It's the same thing as the number of mole divided by the of species I divided by the total number of moles. And clearly Xi, it's a fraction, runs between 0 and 1. And if you sum over all Xi, the sum of Ci is C, so the sum of Xi is clearly 1. So remember, if you use mole fraction, they have to sum to 1. It's a constraint on those species. Similarly, we can define the mass fraction as Mi divided by M, and the notation is usually Yi. And so if we divide the numerator and denominator by V, it's the same as the density rho I of species I divided by the total density. And so the mass fraction, again, it's a fraction between 0 and 1, and the sum of all Yi is equal to 1, which again follows from the definition. Now, since the sum of Mi is equal to M, and since we can write the mass of species I as the number of moles times the molecular weight, right? If we substitute for Ni Xi times N, right? We use the mole fraction, so it's X times N. N is independent of I, it's pulled outside. What we have is a quantity which is the number of moles times something equal to the mass, so clearly that something must be the molecular weight of the mixture. And so that's one definition of the molecular weight of the total mixture, which is the weighted average, but the weighted based on mole fraction of the different species. Now, there is another important relation that we want to establish, and it's a relation between Xi and Yi. And so from the definition of Yi, it's the mass of species I divided by the total mass. Again, we use the fact that Mi is Ni times the molecular weight, and we use the fact that Xi is Ni divided by the total number of moles. So immediately we have here a relation that relates Yi to Xi or Xi to Yi. Okay? Remember that W was a summation over all I of Xi Wi. So it's not, this W here involves all the I's, which is important when you differentiate these quantities, because it's not a constant, and sometimes one may forget that. So with this definition now, there is, or with this relation rather, there is another way to express the total molecular weight of the mixture. If we look at if we start with this definition, we want to multiply xi times wi and sum over all I to obtain we want to come here and use the fact that the sum of xi wi is yi times w, or rather yi divided by wi, which is this. If we sum this over all I and now replace the yi over wi by xi over w, w is a constant pulled out. The sum of xi is 1, and so that gives you another relation for the molecular weight of the mixture, which is the reciprocal of the sum of yi divided by wi. Not the product, but the ratio, which is different than the expression in terms of the mole fraction. Okay, so the first, now we have established some notation and we know how to describe the mixture, and so the next thing is to write the conservation law. And what I will do, the approach that I've taken to make this quick and comprehensive is essentially to use what we have learned or what we know from a pure substance and to apply it to the mixture. So if we if we focus on species I, on one species, and we write the conservation of mass, it's going to be d by dt of rho I, which is rho yi, plus the divergence of rho I vi, which is rho yi vi, right? I'm replacing rho I by rho yi. In this case, it's not conserved, so it's not equal to 0. Rather, it's equal to the rate by which species I is created or destroyed. And so, this is denoted by omega I. So omega I is the net rate of production of species I. Of course, everything in this equation is written per unit volume, per unit time, and so that's the definition of omega I. And so we have n such equations, okay? Now, Vi is the velocity of species I in the bulk. And that velocity is not necessarily the velocity of the whole bulk or the fluid velocity. There's a difference also between different VIs. Different species move at different speed. And so we first define the mass average velocity, and this is defined as V. So that's going to be the velocity of the bulk, the fluid velocity, which is the mass-weighted average of the different VI. Yi, Vi, sum over different I, right? And the difference between Vi and the mass average velocity is what we call the diffusion velocity, which is denoted in my notes as capital Vi. So the diffusion velocity is Vi minus V. In other words, is the velocity of species I relative to the velocity of the whole fluid. Now, if we sum over all I this expression after multiplying by Yi, since the Yi Vi is equal to V, clearly the product of Yi times the diffusion velocity must equal to 0. And this is an important constraint to remember. Essentially, it states that the net flux of the net diffusion flux is 0. If one diffuses into another and so on, the net flux is 0. So now we it's not convenient to have in the equation the individual velocity. So rather we introduce the velocity of the fluid and the diffusion velocity. So we replace the Vi by capital Vi plus V, and that's what's written here in this part of the equation. Now, if these are conservation equation for individual or balance equation, it's more precise, for the mass of every species I, clearly if we sum them all, we should get the conservation of the whole mixture. And indeed we do. In other words, if we sum over all I, this quantity, because the sum of Yi is 1, reduced to d rho dt, and these quantities here with the help of this constraint, and again the fact that yi sum to 1 reduced to the second term, and the sum of all omega I must be 0 because by exchanging when a mixture, the different species just are created or destroyed, it doesn't produce more mass, so it doesn't destroy the existing total mass. So clearly omega I is 0, a relation that we are going to see again later on. So the next equation here is, well, the top equation is what we had on the previous slide. And what I have used is the product rule on the first term, which gives you, of course, this one and this one, and then the product rule on the first term in the divergence, which gives you this and that. And so what is left is the second term in the divergence, which is here, equal to omega I. Since this is mass conservation, then essentially the equation reduced to the time rate of change of the species, the mass fraction yi, plus this flux of the diffusion flux is equal to omega I. Now, there are only n minus 1 such relations which are independent of each other because the sum of the yi must be equal to 1. And so I can apply this only to n minus 1 equation in order to avoid redundancies in my overall equation, a comment that I will make again later. And of course, the sum of all this is this, so if you use that, you cannot use all the n. That's basically the same statement I just made.
Question? Yes.
Yes.
So that is not a tensor notation, right?
I'm sorry?
The yi vi in that equation is
Yes.
not a tensor notation, right? It denotes the species number. The
This
delta
is-
rho yi vi, that
Yeah.
doesn't denote it's a summation of over all yi, right? It's not a tensor notation, right?
It's not a summation. No, there is no summation because this is a vector. This is a vector notation. We use summation convention only if we use index notation. But in fact, I will not use from now until Friday afternoon, not using index notation. Yeah, good point. Otherwise, 0, right? So this is this is the species equation. Next, we want to write a conservation of momentum for the entire mixture. So we start with, in fact, writing which is not written here. We start with the momentum equation for the separate species for every I, and then you immediately see that when we sum them over all I, the left-hand side of the equation is formed. Similarly, when I sum for the equation, think of this, that there is an I here in every term. So similarly, if I write here grad pi, if I sum over all I, and I use the fact that the sum of all the pi is the overall pressure, which is essentially known as Dalton's law, then you get the first term on the right-hand side. This term here is essentially the sum of the sigma I multiplied by different mu I, which are different viscosities, right? But again, since we can define the sum of the separate, we can, by properly defining mu as being the mixture average, you end up with a term which is essentially the divergence of sigma, where sigma is now the stress, the viscous tensor of the viscous stress tensor for the whole mixture, right? So, which is, as I said, the sum of the separate viscous stresses. Then this term here, and sigma is expressed in this form where mu and kappa, which is the bulk viscosity, are now mixture values. In other words, they are mass-weighted quantities. So the mu is the sum of mu I, yi, for example. Okay. I want to avoid these details because they're not going to be important in my discussion. I want to shorten it. And now in your notes, there was a comment here which I forgot to take out. and basically it says something about the gravity is the only force. I didn't mean to say that because when I added here Fi is the external body force acting on species I. So that's in addition to gravity. There is additional forces, in addition to gravity, there are additional forces that, like electric forces, that could be acting on one species and not the other. For example, if the chemical reaction produce ions or electrons that are there are electric forces acting on them, and the forces are different from each other, then they will contribute to this term. Okay? If there were no such body forces, then this term, the Fi acting on all the species, will be gravity, which is G, and so the sum of Yi is 1, and so that term reduced to simply rho G. Right? Okay, the next equation is to again start with a separate equation for the for the total energy of the different species, and sum them to produce the energy of the entire mixture. And so this was the equation that we have written before, and so if we sum them, we obtain now the total energy of the mixture, which again, if we remove the kinetic energy, is going to give you the time rate of change of the internal energy, right? Multiplied by rho. This term, remember, after removing the counterpart in the kinetic energy, produce these two terms, which is the pressure work and the viscous dissipation. Minus divergence Q is here, and here again you have a term which appear in the energy equation only if you have forces that are not applied, or forces that are not acting equally on all species. So for example, if the only force is gravity, you see that this term is replaced by that, but since the sum of Yi, Vi is 0, it adds up to 0. So in the energy equation, if the only force is gravity, this term is absent. If there are some electric forces, say, acting on some species, then there will be a contribution here. Okay, so this is the equation in terms of internal energy. In terms of enthalpy, the only difference is, as I mentioned before, it's only in the pressure term, which takes a different form, right? Now we need to really define more precisely internal energy of the mixture and enthalpy of the mixture. And this is done through, again, going through thermodynamics. The first thing we note is that because we have a mixture that consists of n fluids, then the system is depend on two quantities like before, plus n minus 1 quantities that describe the mixture, right? Not n, but n minus 1, because they have to sum to n. So they are only n minus 1 linearly independent. So overall, it's n plus 1. So for example, if you are assuming that each of the n species is an ideal gas that satisfy Pi equal to rho I RT divided by Wi, okay? Then if you sum that over all I, you obtain the total pressure. Remember, that's Dalton's law. Rho RT times the sum of Yi sum of Yi divided by Wi, because rho I is rho Yi, right? So you get Yi, and this is exactly 1 over the molecular weight of the mixture. But this is the quantity that I want to focus on to show you that it depends on 2 rho and t plus n minus 1 Yi's. Okay, so through this example, we also have now an equation, or an equation of state for the entire mixture. Okay, remember the W depends on the composition. It's not necessarily constant in general, even though we often assume that it is, but we're going to get to that later. The internal energy is expressed as the mass-weighted internal energies of the different species, EI, and so is the enthalpy H of the mixture, which is defined as the sum of yi hi. And the relation between hi and ei is like we have seen before. That's essentially the definition of hi. So it's ei plus pi over rho I. So that's valid for any n. Now, if we assume again that our mixture is an ideal gas, as we are doing now, then the ei are only function of temperature, and so are the hi. And therefore, we can write that ei is ei naught, an integrating constant, plus the integral of Cvi dt, where Cv is the specific heat at constant volume of species I, and Cp is the specific heat at constant pressure of species I. Now note that those reference values may be different and are different for each species, and so we have to keep track properly of what they are, and we're going to see that later on. So now we know what ei and hi, and so we know how to construct the internal energy and the enthalpy of the mixture, E and H. In general, what did I have here? Yeah, in general, those Cp and Cv, right? But once you know one, you know the other. They are a function of temperature, right? That's why we need to integrate them over temperature here. And they are a function of temperature, and that dependence can be found in, it's tabulated. They are known as the NASA polynomials, which they approximate those quantities, so the temperature dependent of those quantities. In those NASA files, they are usually, it's the CPI expressed in terms of the molar heat capacity rather than the mass heat capacity, which I have been using until now, and hence the molecular weight that appears here. And the quantity Cp over rho, which clearly has units of temperature, is written as a polynomial like this, with the A1, A2, A3, and so on. They are tabulated, and you can find them when you need them. Okay, so it was a really more of a side comment. I would not need this in the future discussion that I will carry on. Now, one can also define a specific heat, Cp, for the entire mixture, again, as the mass-weighted specific heats of the different species, Cpi. So Cp is the sum of Cpi yi. And so now the enthalpy, which is defined as hi yi summed over all I, can be, if you replace hi with the specific enthalpy plus what we call the sensible enthalpy, it's going to be the sum of yi hi naught plus the sum of yi times that integral. Okay? But essentially, this integral, or the sum of this, is the same as the integral of Cp, where Cp was defined here, because the definition of Cp is at constant composition. And so one can write that the total enthalpy is this sum plus the integral of T naught to T of Cp. But remember that this quantity depends also on the yi, because the Cp depend on the yi, which is important when you differentiate it, as we shall see soon. Okay, so now just a few words about the specific enthalpies hi naught, and we have to define them in a consistent way, those reference values. And so for each species I, the reference enthalpy is chosen as the heat of formation at some standard temperature T naught. And the heat of formation is the heat evolved or absorbed when 1 mole of a substance is formed from its elements, okay, important element, at the standard state. The standard state is essentially room temperature and atmospheric pressure. So for example, if you look at the formation of water, okay, it's formed from H2O2, and since this is an exothermic reaction, then the change in specific enthalpy is negative, saying that there's amount of heat that is taken away in order to form water. And all these values are tabulated. This is taken from the book by Glassman and Yetter. And you see here is the what I have just shown you before. So the change in the enthalpy of formation is minus, what is it? 15.84. And by the way, you should note that there is another water here, which has I'm sorry, there is another listed line of H2O, which has a slightly different value. It's minus 13.44. Of course, this is because this is the formation of water in liquid state, and this is water vapor, and the difference is the latent heat of vaporization. Now, another thing is, by definition, all oxygen, nitrogen, they are in their basic state, and therefore the enthalpy of formation is 0, as it should. So that essentially covers all I was saying here. One more thing. However, so by definition, the heat of formation of the elements like hydrogen, nitrogen, oxygen is all 0, but oxygen atom, however, have a non-zero heat of formation, and this is because you need to break O2, or a molecule of oxygen, to form, right, atoms of oxygen, and that require this much heat. Okay, so this is one thing. Now, knowing the heat of formation, we can define the heat of reaction at a constant pressure for a more general reaction, but at the reference temperature T0. So for example, if you have here this relation, which is methane plus oxygen gives you CO2 and water, the heat of reaction at 298 Kelvin can be found by just the difference in the enthalpy of formation of the product minus those of the reactants. And the bar here just denote that it's per unit mole rather than per unit mass, which was my previous notation. And so if you look at the table and you see the heat of formation of CO2 is minus 393 plus 2 moles of, plus 2 mole of water, which is minus 241 and so on. Take the difference, that gives you the heat of reaction at T0, at 298, at room temperature. Now, if you know it at one temperature, you can calculate at a different temperature, because HI of T is going to be the heat of formation plus the integral of CPI dt, and those CPI are tabulated, so this you can find. Okay, so this was just to get a little sense of what these quantities are. Back to the general equations. We have so far an equation, a continuity equation for the entire mixture. We have a momentum equation for the entire mixture, and I have removed here, I said that somewhere? Yeah, no, where the body force, there is no other body force than gravity, right? In other words, if there is something else, there is a contribution here, but I'm not going to use this in my lecture, so I took it out. Then we have the species equation for the different yi's, where this quantity remained to be determined, the rate of production consumption of species I. We didn't define that yet. In the energy equation, we did not define yet what this heat flux vector is. And by the way, I forgot to say that we also didn't define yet what the diffusion velocities are. And and those two equations are equivalent. You use one or the other. I just wrote them both. And then you have the equation of state and the definition of H. So in principle, we still have to talk about, we need constitutive relation for the diffusion velocity, for the rate of production consumption, which will take us into chemical kinetics, but we need constitutive relation for this VI and for Q, and this is the subject, I believe, of the next slide, but I think that we ought to take a short break and then continue. I have some really more material than the time, but then the lecture are not exactly balanced. Some of them are a little longer than others, so I'll try to balance it somehow.